Hi, and welcome to Calculus Examples. I'm Dr. Finch. Today we're going to look at an example where we're finding the values of two numbers, A and B. We're going to use letters to represent them right now, such that the following limit exists. Where x goes to 0, we're looking at sine of 2x over x cubed plus a plus b over x squared. And I'm going to apologize a little bit in advance. This is going to be a little bit of a beast, but it is going to be really interesting. So we want this limit to exist. Notice if we plug in 0 as we normally would to start off with, we have a lot of issues popping up. One thing that we're going to do before we even go any further is we are going to turn this whole mess into one single fraction. So let's start off by doing that. We'll take our limit as x goes to 0. And our common denominator for everything, you'll notice, is going to be x cubed. Now, you can probably do this in one step. I'm going to do it in two different steps so that we see everything that's going on here. In our second term, to get an x cubed in the denominator, we're going to multiply by a fancy one. So that's x cubed divided by x cubed, right? And in our third term, we only need one extra x to get an x cubed on the denominator. So we're going to multiply the top by x and the bottom by a single x. All right, and now let's smush this. So we have one denominator x cubed, sine of 2x plus ax cubed plus bx. All right, now that we have this done, it might be a little bit easier to see what's going on here. If we plug in 0 for x, right, we get 0 in the denominator. We get sine of 2x, and I'm not a big fan of memorization, but there are a few things that you should memorize for any calculus class, and one of them is what sine of x looks like as a picture, just so that you know when you plug 0 into sine of x, you get 0 as an output. So knowing some of those basics can really help out. 0 times a is 0, 0 times b is 0, so we get 0 over 0, right? And this tells us it's unknown, but it's a very particular type of unknown. This is a setup for L'Hopital's rule. And hopefully you've seen this before. If not, I encourage you to go and read about it. We are going to be applying that a couple of different times today. So L'Hopital's rule says when you have 0 divided by 0, which tells us we don't know what's going to happen with our limit, we can take the derivative of the numerator and the derivative of the denominator separately, and you are going to get the same exact limit. So we can just substitute that in there, which is super duper useful. Let's start with the derivative of our denominator since that's going to be a little bit easier. X cubed, we bring our exponent down, subtract 1 to get our new exponent, so that's 3x squared. In our numerator, derivative of sine is going to be cosine, but there's a little bit of a hitch here because notice we have 2x on the inside here, right? And so when we take our derivative, we're actually going to be using the chain rule here. So derivative is also going to be derivative of that inside bit, and the derivative of 2x is just 2. So we need a 2 cosine of x. So not only are we using L'Hopital's rule, but we are also using the chain rule. Next up, remember a is a number. We don't know what number that is, but it is a number. So we are going to just leave it alone. We're going to bring that 3 down and subtract 1 to get our new exponent. And then a number times x, the derivative of that is just going to be a b. All right, so let's see. At every step when you do L'Hopital's rule, you want to plug in your limit and see what happens when x goes to that value, just to check and see if you can stop applying L'Hopital's rule, or maybe you can't anymore. Sometimes you can't. So this is going to be cosine, 2 times cosine of 0 plus 3a times 0 squared plus b all over 3 times 0 squared. All right, so here we have another situation. Here's the second trig function that you really do need to know for calculus. It's a nice thing that you can get away without knowing too much trig, but there are some things that are super important. So cosine of 0 is going to be 1. 1 times 2 is 1. So we have 2 on top. And then we have our b value that survives as well. And we have a 0 on the bottom. Okay, so now we're in a little bit of a bind here. We have 2 plus b over 0, and we want to know what's going to happen with our function. So I'm going to draw out a picture of kind of what we're going to look at. Here's one more graph that, and unfortunately this isn't the last one, but this is a really good one to have in your head. Y is equal to 1 over x. So you'll see now when we look at this graph, as x gets closer to 0, right, as we come in from the right-hand side, we go to positive infinity. As we come in from the left-hand side, we go to negative infinity. And if you modify this little graph a little bit by putting a different number up here, remember b is just a number, so if we put in like the number 1 for b, that'd be 3 over, essentially this ends up being 3 over x. And you are still going to have a graph that's going to be very similar to this. And so our function, because of the way it looks, the limit does not exist unless there's one place where the limit is going to actually exist. And that is going to be when b is equal to negative 2. Now, why is that? Because when we have 2 plus b over 0 and b is negative 2, then we get 0 over 0 and we are set to do another LHOP on this. So that's why our first condition is going to be b is equal to negative 2. We wanted to know what values make our limit exist. If b is anything other than negative 2, you can see what's going to happen here is as x goes to 0, this term is going to go to 0, this term is going to go to 2, and we'd have 2 plus some number over something that's going to 0, which is going to look like this. So, whew, that was a lot. Okay, so here's our first thing that we need to have. Let's do our L'Hopital's rule again. So we have limit as x goes to 0, and we are taking the derivative. I'll do this in several parts. So we have 2, and then we have the derivative of cosine, which is going to be a negative sign. But again, look at that. We have a chain rule that we're going to have to use. The derivative of the inside is going to be a 2, so I'm going to pop another 2 out front. Plus, we are going to do 3a, bring that 2 down, subtract 1 to get our new power. B is just a number. In fact, b is negative 2, so that's going to vanish when we take the derivative of our numerator. So we're left with only 2 terms on top. And in our denominator, we bring our power down and we subtract 1 to get our new power. All right, let's clean that up just a little bit because it still looks a little bit messy. I'm going to put our negative sign out front. 2 times 2 is 4. So we get negative 4 sine of 2x plus 6. 3 times 2 is 6. 8 times x over 6x. All right. Now we again plug in what happens to 0. Sine of 0, as we saw before, goes to 0. If we have 0 times 6a, that's going to be 0. 0 times 6 is 0. So this is, again, set up for another L'Hopital's rule. All right. I swear this is the last one. We do need a new page, though. Okay, so we're going to LHOP one last time. Let's put our limit out front. As x goes to 0, we had a negative 4 that's coming along for a ride. Our sine turns into cosine of 2x. And again, we have to do the chain rule, so we're going to multiply by another 2. Plus, derivative of 6ax. Our x is going to disappear. Our constant, which is going to be 6 times a, sticks around. The derivative of our denominator, 6x, is going to be a nice little 6. So this gives us the limit as x goes to 0 of -8 cosine of 2x plus 6a all over 6. And as x goes to 0, we know cosine of 2x is going to go to 1. So this is going to be a -8 plus 6a over 6. And you can leave it like that, or we can reduce it a little bit, make it a little bit prettier, because you'll notice we can cancel our 6's out when we break that into two separate fractions. And -8 over 6, they both have a copy of 2 in there. So let's divide out by 2 on the numerator and the denominator. And we get -4/3 plus a. So our answer, or a solution to this problem, remember, we were asked what a values and what b values were. We need b to be equal to -2 and any a value, because we noticed we never came up with a restriction on our a value in this problem at all. So those are our two things that we needed at the end to figure out what is going to make this limit exist. And that was quite something. So thank you for joining me on that journey, and thank you for listening.